points we've ever seen in not just this industry, but probably any industry. We've got inflection points coming on almost every level that you can imagine, from EUV to lithography to new transistor types to new market types. What's your view of what's happening on a big picture, and how will that change the industry?
Well, I think sound. There's no sound yet. It's hard to have an opinion without sound. So much for the transition.
He's coming.
No sound.
We have an inflection point on microphones too, so.
This is a planar transition.
Uh-oh, we've got the old standby.
Does this one work? Yeah. Okay. I guess we went from planar transistors to FinFET and a few yield issues here. There's no question that there's an enormous inflection, or no, it is a continuation of the same exponential evolution of technology and its impact on mankind. I always like to look at the semiconductor industry as so far having had really only two major phases. The first one was computation, and the killer app was the PC. But after that, it continued with the internet, with servers, with the cloud. Put that all together as computation. Still continuing, obviously, and with big data will continue massively, but has fundamentally flattened in terms of its economics. The second one, after a fairly major semiconductor break in terms of growth rates, was mobility. Killer app, clearly the smartphone. And the smartphone was then, of course, the platform for enormous numbers of applications. And so both of these phases have had big growth, have had amazing pushes on technology, and have been the platform for many other people to make impact, mostly the software world. And these phases, while not ending, have just flattened somewhat. And now you opened with really technology changes, but I think the much more interesting change is how the relationship between the hardware platform and the software is changing towards an opportunity to, for the first time, truly look at digital intelligence as now becoming practical, possible, cost-effective, and clearly being as big a transformation as we've seen in the first two. The whole computational age brought productivity, massive productivity change for mankind. The mobility age really brought globalization through communication and access to data information in a way that transformed everything. Digital intelligence will transform everything again. And so why does it not feel like it's up to the right yet? Well, because multiple things are coming together at the same time, but are not here yet in large volume from a semiconductor perspective.
So we tend to characterize this as the Internet of Things, which is where you're going with some of this, right? But it's really a number of very discrete markets that are developing at their own pace.
So I actually don't like to characterize it as Internet of Things, because Internet of Things, while unbelievably promising and connecting everything in the world to the Internet in some way, is ridiculously small silicon. And a little IoT is this size, and you can't fill many wafers with that. Now, it does create an enormous amount of data. The question is, what do you do with it? And there are two ways to do something with it. One, through the big data, so the computational angle, the cloud. But the other is local utilization of the data and some degree of smarts. And I purposely don't use artificial intelligence, because that relies on saying, well, we're going to be like the human. There's some pieces that are like the human. There's some pieces that are not at all like the human. Take a simple example. Humans don't have, X-ray vision, notwithstanding, the magazines you and I read when we were kids, where you could buy these glasses that were very promising. But the fact is, cars do have infrared vision, for example. And so the digital intelligence will be broader and narrower than the human, but very fundamental. And automotive industry is interesting, because here's a very slow-moving industry that has suddenly turned to turbo speed in adopting smarts in a fashion that's unbelievable. Cars are actually driving around with already fewer accidents than humans. That's pretty cool.
Let's back up here a little bit. So when you're talking about Internet of Things, the initial version of the Internet of Things was lots of dumb little devices scattered around. But what's showing up as reality is much more purpose-built, very sophisticated device for processing at the edge, because you just can't, it's too expensive to send this data, whether you're talking about power or performance. You have to do some of this intelligence, whatever you call it, somewhere on your device. Am I correct there?
Well, I think that's exactly the positive interpretation. The minute you say not dumb device, but the opposite of dumb, and we'll see exactly what it is, you're saying, okay, more silicon, and you say faster silicon, and you say also low power silicon, because it still needs to be close to the actual sensor device or so. And I think this is precisely where the minute there are a couple of killer apps, this thing will be running very, very fast. But it's also clear that economically right now we're looking at a few more years before the economics are felt in the semiconductor industry.
Okay, now that we've got a common language here, so the big problem on all this is really what do we do with all this data, right? Because we're managing huge quantities of data at a level we've never managed it before. Is that one of the big changes that's coming?
So this is where we need to think exponentials, because you can say, yeah, we've never seen this much data, and of course that's true, except that that's been true ever since Moore's Law. The essence of Moore's Law is exponential change in things. And as a human, we can understand it, but we don't feel it. Everything we feel tends to be more linear. And so when you suddenly see twice as much data or 10 times as much data, to feel that feels like a lot. But if you reason it and you say, well, no, that's exactly the curve that we've been on for a long time, it's a continuation of that curve. Maybe the astounding part is that, notwithstanding what many predictions have been, is that another 10x is still possible. And I would argue is still possible a few more times.
Okay, that data that you're talking about that is increasing sort of linearly is also increasing in 3D if you take a look at it from a matrix standpoint, right? Because now you're not just processing out of one device, you're processing everywhere. And all this data now has to be managed in many different places.
I think it's much better than 3D. 3D, you're just taking the visual part, right? 3 dimensions, different cameras, different thing. But why not at the same time measure the temperature or whatever you see? There's many other things that you can see. So there's the potential for many more dimensions, so even more data. And even more data means more processing, including concentrating data in something that's manageable and that's cost effective. And at the end of the day, everything is governed by techonomics. The balance between what you can technically do and what you can economically leverage.
So this is great for everybody in this room.
Absolutely.
I mean, there's lots of opportunity coming forward. Now the question is, we talked about Moore's Law, or you talked about Moore's Law. I want to talk about Moore's Law. How much life does it have left in terms of how many people are going to be pushing down to the next node? How many more nodes after that? Because we do start dealing with some fundamental issues of physics.
Well, you and I talked a few minutes ago about death of Moore's Law and habeas corpus. Show me the body. I mean, this thing has been predicted dead many, many times, and it has found ways to circumvent death in ways that were completely inconceivable just a few years earlier. And this, the first massive breakthrough was really in the 90s, where it became possible to do photolithography below the wavelengths of light. Well, that was unimaginable, because photolithography, the very thing, is the wavelength of light that determines things, and yet we do this, right, massively. EUV is just a reprieve for that again, but I would argue that 7, 8, 9 years ago, it was completely clear and proven that FinFETs would never work, would be too difficult, too expensive, too narrow, and so on. And here we are, right? 16, 14, 10, massive push on 7, development on 5, in the works as we speak. And so from a production point of view, I have no doubt we have another 10 years that we can already see today.
The time between nodes seems to be slowing a bit, though. There are more things that you have to do at each node that you didn't have to deal with in the past, right?
Well, let's not forget that the definition of node is a marketing event. And so the if you say node and you don't say yield, you've stated half of the description. And so there's no question that the complexity of what's being done, and therefore the investments around that, and I think you're heading towards that, has grown with the complexity or the smaller size of the nodes. Just this morning, I saw a little graph that showed 28 nanometer to 16, 10, and 7, and it was remarkable. It's like an 8x decrease in size. 28 is not that long ago, and it is the most popular node today.
And people are doing a lot more with these nodes that exist as well. So even at 28, we now have multiple flavors of that node, multiple flavors in terms of process. There are new materials coming in terms of FDSOI, which is also going to 22. We have new ways of architecting some of the packaging on this. This is all lots of different pieces and ways to go that are not just a straight linear path that we've been following.
Well, that's the interesting part of techonomics, right? Which is any technology has its own economic cycle. And you're absolutely right. A lot of people started to bank on 28, partially out of the reasonable fear that FinFET would be pretty wobbly for a while, and pushed on 28 in many different dimensions, all the way to having now specialty areas that may apply to automotive and others emerging there. And so, squeezing out the maximum of a node is a good thing. Driving the state of the art is a good thing. The balance between the two is economics.
One of the things that hardware engineers have to deal with a lot more these days is, or at least their compatriots, is more software when they develop a chip. It's not the same as it was 10 years ago where you come out with the hardware and somebody else develops the software. Now the software not only has to be done, it has to be done at the time the chip is done. It's probably developed internally, and the people that are coming into the market now, because we obviously are a somewhat graying industry, and yes, I know you always throw that back at me and say I've
Speak for yourself.
I've been there before you. But as we move forward, the new people that are coming in are learning different things. They're learning things like Python, Java, and it's not the same way of looking at a chip. Does the software now drive the hardware, or will it in the future, or will the hardware drive the software still?
So I think it's a super interesting question, because there's no question that in the first generations, once you had basic generic hardware, a lot of people figured out how to do something in software. If you want to do another, not 5x, but 100x improvement on something, you will adapt the hardware to the software. And that becomes more and more possible. And I think it's going to be very desirable for certain specific digital intelligence applications. Because the minute these applications become sort of viable, what's better than something smart? Something a lot smarter. And a lot smarter is 10x, 100x in computation. And I think we will find ways to deliver that, banking on one hand on the sophistication of the silicon, which will still be at a premium. And there's a lot of people pushing on advanced nodes in remarkable ways as we speak. By the way, as a little side note, it's remarkable how the automotive industry has discovered that FinFETs are actually viable transistors. And they are putting a lot of effort in a variety of data processors, all aimed at one thing, which is drive the car better, right? And so I think the push will come from both sides, but the intersection of hardware and software is going to be at a premium in terms of how well you do it, and how well you assure that the notion of yield sort of applies to software too. Except yield is not volume dependent, it's directly related to the number of lines of code that you have.
We've been talking for a long time about hardware, software, code design. Are we actually getting there, or are we sort of slipping the other way now?
Oh, I think we're absolutely getting there. And we can see that in our verification business, because the verification capabilities in the last 3-4 years have made unbelievable steps forward, mostly because many different techniques that work at different levels of abstraction have come together in a much more integrated platform-based way. So, for example, you can compile directly into simulator or the emulator or into a virtual prototyping type situation, and combine those, and now bring up software on hardware that you don't have, which is perfect because that allows the software guys to move forward while the hardware guys are slaving on their part, and hopefully get everything ready sort of at the same time. Not clear who's slaving most, but everybody's slaving in our business. So the ability to essentially mimic a hardware-software system has advanced by leaps and bounds. At the same time, where the amount of code has grown non-linearly, and of course with that comes all the challenges of quality control.
Well, quality control is one of the big issues here. Basically what you've done when you do improve hardware, software code design is you eliminate one of the companies that can be blamed if something goes wrong between the hardware and the software. Wasn't as much of a problem when we're dealing with a smartphone, but it's a whole different problem when we start dealing with automotive embedded code where this stuff has to last for 10 to 15 years.
Well, actually you're putting your finger on something very important, which is many of these systems are close to the personal human destiny, meaning they drive...
Or cause it.
Or the end of that destiny, exactly. And so, a car is a very different device than a cellular phone in terms of the sheer regulations that apply to making that thing viable. And so the automotive industry is a perfect example of an industry that for 30, maybe more years, has legislated itself in terms of a number of standards that you had to meet. And reliability is an important one, but it is one of the later one compared to first making sure that you have mechanisms to find faults and know what you would do if there were faults in the chips. And so, you're all familiar with ISO 26262, for example, but there's a zillion other that one has to live up to. And it is only recently that this has suddenly yielded a number of alerts in the software world. Because we should throw in one more thing, which is security in this, and the fact that the Jeep was hacked last summer, despite the fact that automotive has been unbelievably safe from a technology point of view, suddenly security became the weak link in safety. Well, that means immediately that's a continuum of engineering, and therefore these same techniques need to apply. And so for that reason, one of the things that at Synopsys we're pioneering is the notion of software sign-off. Meaning that one should be able to check, at least for all the type of issues and errors that are known automatically and comprehensively.
And one of those errors can be if there's a vulnerability in the software, right, for attack or hacking.
Yes, absolutely.
That's brand new. But the other piece that, as we move forward down this line of thought, can you be sure that when you're developing the software that it's the software that's causing the problem versus the hardware? Does that finger pointing now come inside, and do we have the tools and the capabilities in existing systems that we've been working with in order to be able to make all that work?
Well, finger pointing is mostly a psychological, technique, let's say, and so
Don't tell that to your lawyers.
I'm sorry.
Don't tell that to your lawyers.
Well, let's not even go there. They're professionals. The finger pointing doesn't work so well when you have multiple people to point the finger at, because they will start pointing the fingers between each other and you get a mess. But the fact is, everything we do has long been a team sport in high tech, and great companies try to find ways that don't result in finger pointing as the mechanism to either diagnose failures or do something about it. Having said that, I think there's another reason why in semiconductors there's more and more software. And as a matter of fact, in the last 10 years, and I've been tracking it somewhat, if you ask what's the ratio of hardware to software engineers in semiconductor companies, I'm not even speaking about system companies, it's easily 3-to-1 today in favor of software guys. And of course, the semiconductor guys always say, well, and it's hard to get money for it. But the fact is, they're selling functionality, right? And so therefore you own some of the responsibility to make sure that you deliver against the spec that you advertise. But it's also true that, especially with security, there's an other angle. You know, in all the other situations you say, well, I'm fighting with physics and I'm fighting with good design, but at least you're in control of your destiny. With hackers, you have actually proactive forces that push back and try to find holes, and then use the holes in some cases for really bad intent. That is a dimension of ongoing battle that's not going to go away quickly, and will demand a very high degree of being on the ball to continually deal with this.
Do the tools that exist today, are they capable of dealing with these problems? Is it a methodology issue? Is it a question of we need new tooling that has to go forward?
Yes, yes, and yes. Meaning that these capabilities can find an enormous number of things. Methodology is mostly the part that orchestrates human discipline. And so you can put the emphasis on the word discipline, or you can put it on the word orchestration. Ultimately, a good methodology requires less discipline because it automates it, but discipline is needed to put methodology in place. And so this is evolving as we speak very rapidly, against a backdrop where the intrusions, or let's say the creativity of breaking something, which is not necessarily a bad human creativity, but can be negative in its impact, is very active right now.
You bought a couple of high-profile software companies, Coverity, Codemonic. What did you learn out of that surprised you, that you didn't expect?
Well, first, that we are still at a very early stage of structuring those methodologies for software development. And in some ways it's strange, in some ways it's not. And because one can explain back to economics. It's strange because I remember, even going through school or early days of Synopsys, where Carnegie Mellon had sort of these ratings of good software development, and you say, okay, that should have, continued for 30 years. We must be in pretty good shape. Well, I think it's the economics that push back. So if you look at the difference between checking out hardware versus software, we all use the term sign off, with a very clear understanding that that's the moment that says, I'm going to go tape out and give it to a foundry. And at that moment, the bill just took a step up of a few million, and then a long commitment, right? And so the sign-off is a very distinct and conscious step. In software, I don't want to say it compiles, so ship it, but there's some of that that goes like that. And so let's say there's an issue, a bug, what do? Well, you ship out a patch, right? And what if the patch creates a problem? Well, you ship out another patch. That's why we're getting patches every other day. And if it's not on life-critical things, you can say, well, we can live with it because the economics are beneficial. But that is now completely changing. And it's completely changing because, A, it's starting to touch more and more life-essential devices. But the other thing is, it's starting to touch things that touch things that touch things that touch life-essential devices. With other words, this notion of Internet everything says that things are no longer in isolation. I used to make the joke a number of years ago that people that install these systems at home, they need to watch out because sooner or later the perp would come in through the toaster. That was a joke. And then you read up on the Target break-in. The perp came in through the air conditioning system. The break-in into the Jeep, the perps came in through the radio. Innocuous parts of the device.
So when you're dealing with verification of software, you're dealing with coverage metrics the same as what you are in hardware, but they're a lot harder to evaluate. First of all, you have more users, and second of all, they change over time as capabilities change.
Yes, and actually that is going to be one of the most difficult things, because let's say, for argument's sake, we have a methodology that truly could capture all bugs and all security issues. We don't have that, but let's say we did, right? You ship your product, and now a new hack is discovered. We have a capability today that allows us to help our customers find in binary code the fingerprint of open source software. And by the way, there's a registry of open source software with known vulnerabilities. It gets updated all the time. And so, again, let's say you've been diligent, you've checked this all out, and you've shipped your product, and now a new one is discovered. We can inform you, hey, sorry, the bad news is, in the thing you just shipped is now a new vulnerability. Do you want to know? Do you want to let your customers know? There's all these type of questions. But the fact is, these are now moving targets. And, okay, that will bring about a set of interesting challenges of how we deal with it.
Like a software download to your pacemaker.
Pacemaker is a good example. I remember a large company, this is in my earlier days, that had acquired a pacemaker little company. And they divested it because that large company could not take the risk of insurance of that little pacemaker killing some people. And so, good example of not only tech-onomic, but tech-legal-onomic circle, right? Everything ties together. And so, okay, we have the privilege of being in the middle of an industry that changes the very nature of mankind and its opportunity space. Okay, well, let's embrace as much as possible the challenges, ethical or otherwise, that come with it. That doesn't mean we have the answers, but I think, this is among the brightest audiences in the world. We should deal with it.
One of the new things that's entered in here, correct me if I'm wrong, is that we're now looking at markets that really do start tracking reliability over time. And reliability is actually a measurement over the life of a product, but that product now is much longer, it's much, as you're saying, much more life critical. How do we do that? We have no experience in, as an industry, in saying this is going to last for on a fully integrated SoC for 15 years in a life-critical type of situation.
Well, I think this is one of those areas where actually IoT or sensor devices bring great opportunities. There are more and more techniques that, for example, can just look at the sound of some mechanical device and analyze the sound and say, there's a new frequency here, and we know that when that happens, this thing is going to break within a week. That's preventive maintenance. That is a form of reliability, right? Mm-hmm. And actually, just this weekend, it was sort of a dinner party. I proposed the following question. I'll put the question to you. Let's say there's a device that you can have on your body, sort of like a Fitbit type thing, just next generation, right? And it can measure a bunch of things in your body, and it can predict that you're going to have a heart attack or a stroke or something of substantial gravitas. Right? How much would you pay for that if it could predict it 1 minute ahead of time, 1 day ahead of time, 1 week ahead of time, or 1 year ahead of time?
And let me flip that question around to you and say, would they pay more for the EDA tools that would prevent it?
Oh, yeah. We're just the enabler. It doesn't matter. It doesn't matter. I think we are a fabulous industry that has, it is the privilege of driving half of Moore's Law. And I think we should give absolutely full credit to, the technology and the manufacturing. We have been able to harness this Moore's Law towards creating devices that then our customers and their customers have put functionality around that has changed. It has changed the destiny of mankind. Now, hopefully we use it for the right things, but the fact that we can be players in that, and that as individuals we do okay, is its own reward.
You're bringing up an interesting point, though, which is how much more are people willing to pay for a service that, and you start going into gradations of service. So if you don't own your car and you're calling up a car to come pick you up, if you get it within a minute, would you pay more than you would 10 minutes from now? And if you want the clean version, or versus the standard cab where somebody's put gum on the seat and you don't really think about that, would you pay more for that?
Well, I mean, that's a judgment of value. And, my example was a little more gravitas than value, right? My example was destiny, meaning that, there's a prediction of your destiny coming to an end. And depending on the timeline, you have more or less opportunity to do something still about it. The 1 minute means one more phone call. The 1 day means making it to a hospital. 1 year means, okay, completely changing your lifestyle. And so remember, we came from the machine that has to keep working. And again, I don't want to out nerd us in all of these extrapolations here, but the fact is that when you can measure physics in the sense of the word in every which way, I think another way of looking at where we're going as a high-tech industry is ultimately we will be able to model everything. Now, how well is the question, but with a massive amount of computation and measurements, we can model weather. That was impossible, thought-wise, 20 years ago. We can obviously already model games that people thought were impossible to win, like Go. And this is a combination of understanding and being able to grab the data on physics and do something useful with it. Now, useful may be in the local way, and so local smarts or mobile smarts, and all the way to big data analysis and all kinds of stuff will be able to be found out of that with many issues as well.
And what you're talking about here is, to some extent, taking what we've learned in EDA and moving it out onto a big system picture, right? So it's no longer just the chip, it's now how does this apply and interact with other things in the real world?
Absolutely, and so that's why, from my perspective, what we're trying to do in the intersection of hardware and software is so important, because I think the center of gravity is already moved up. The center of economics has way moved up, right? I mean, the fact is, the Facebooks and the Googles and so on are worth way more than the system companies underneath, and then the chip companies. But that's called leverage, and but overall, our center of gravity to provide the next massive wave of impact and application capabilities is in front of us in just a few years.
Which sort of leads smoothly into the next topic that I wanted to discuss. Synopsys has been buying a couple of more TCAD companies. Where do you see that going, and how does that play out in the market?
Well, the interesting thing is, as you move to smaller dimensions, by definition, the physics tighten up, the data management becomes just as important. You have way more data points. And so the management and the computation of what ultimately for practical purposes are the IR curves of the devices, and they're more complex than just IR curves. But in simple terms is, how do I get to a SPICE model before I have the goods? Mm-hmm. And how can I do that in a fashion so that I don't need to do large numbers of fab runs that are unbelievably expensive? So experiment, model the a virtual physical device, and it's a continuation of that. These are not huge markets; they're very specialized, but the root system down in not only silicon but in materials will continue in order to nurture this tree above.
We've talked about a lot of changes that are coming on a wide variety of levels here. How do you, as CEO, structure co-CEO? Where do you put your R&D dollars? Because there's a lot of uncertainty out in the marketplace right now.
You ask your co-CEO. There's infinite debate. There's infinite debate of this or that. It's also very much a function of what talent you may have at any point in time, what circumstances are there. And you try your best to have sort of a balance between existing businesses that have a degree of profitability that's large enough to sustain some degree of investments that are adjacent and a little further out adjacent. And over now close to 30 years, we've been able to find that balance. But essentially, we're in a business that every time you do well, you put all the chips back on the table, literally. all the money goes back into driving technology forward. And how you balance that is I guess a combination from having a lot of friends that give you good advice to some degree of intuition that says, well, now's sort of the right time for this. I always feel that strategy is very simple. Timing of strategy is almost impossible to be right on.
As a percentage of revenue, has R&D gone up because of that?
For us, it's not really gone up. We've been in the low 30s for as long as I remember being asked the question.
Which is also really high for other industries.
I think it's among the highest of any industry. But hey, that's nurturing and exponential. Exponentials are really hungry beasts, right? I mean, that sucker eats 10 times more, or tries to on an ongoing basis. And so either you live with that or you don't. And invariably we get the question, legit question, why can you not go lower R&D? And we can absolutely go lower R&D, and for 3 years you wouldn't notice much. And then it's, well, okay, redo company. Right?
Speaking of that, has the R&D cycle stretched out now? Is it longer on when you invest to when you actually see a benefit?
Generically, yes, and the reason for that is simple, which is we have moved from scale complexity to systemic complexity, meaning that not only are the chips that we do, or any aspect of the chip, let's say the transistor gate count, have gone up exponentially, but we've had the help of better and faster computers and multi-core and all that. It is that the dimensions are all intersecting. And so, this is nothing new in principle. In practice, it's continuing to grow in complexity. But, the trade-offs between, speed and power and time to market and reliability, they're all active trade-offs in many ways. And so, the solutions that we have to deliver to the customers have to work through many, many different tools. And so, a large platform evolution is, 5-year development and a 5-year rollout process.
Do you find it harder now just to be able to do what you used to do with the tools? So in order to solve some of the same problems that you did at 40 nanometers or 28 nanometers, moving down to the real 7 nanometer, will that be significantly harder with existing tools?
Well, let's start with the reverse. If you take the existing tools and you apply them to 40 nanometer, the problem's a piece of cake. So okay, let's take that. By definition, the problems are more difficult because they continue to increase in scale complexity and they continue to increase in systemic complexity. On the other hand, the people working on these problems are actually a lot more experienced and have learned how to be in multi-dimensional optimization for now 40 years. Right? This is an incredible skill. I've got to believe, I don't have hard facts for that, but that our industry delivers among the most sophisticated software ever built. We have 400 million lines of code, not a single bug in it, as far as I understand, and this is a big endeavor, right? And so managing this on an ongoing basis is very exciting because you have to periodically sort of redo things to simplify them again. And every time you do that, you have to deal with backwards compatibilities and so on. But as an industry, remarkably so, I will easily add the next 10 years. We've been at it for, if you take Moore's Law the whole time, that will be 60 years. 60 years of exponential. That's pretty cool.
From your perspective, let me leave you with one question here. What is the next big thing or things that you see coming? We've talked about some of the markets, but what do you think is going to drive a lot of growth similar to at a level of what maybe the smartphone did for after computing?
Well, the challenge with that question is that everybody would like, so what's the one killer app that's going to be a thing? And color apps are not predictable. I remind you, introduction of the iPad, evening before morning after, 80% of the professional pundits wrote, this thing is not that great. You can make really good phone calls on it. Who wants to touch things with their finger? What's this thing about apps anyway? And within months there were 10,000 applications on it, and everybody got it, right? Same for the iPhone. And so predicting the killer app is difficult. Predicting the nature of the killer app, I don't think is. And I would propose that the recipe is, it is smart everything. And then the question is, so what are the first everythings? And the first everythings are going to be things where you have something already of substantial value, and adding smart to it becomes a multiplier to the value. That's why a car works that. That's why a human body is of high value. If you can do anything to improve that, that will turn into a killer app in some way. That's why a container is of good value. A robot is of high value. There's many of these type of things that the preservation of your house, the detection of forest fires. These things are all big dollar ticket items that, enhanced by some smarts, will very quickly economically justify themselves. Now, for the semiconductor industry, the question is, how large is the size of the computational element? I buy the fact that there's going to be a zillion small IoT linked to physics devices. That's just a preamble here. The value creation, or the growth of the semiconductor industry, will be linked to how much smarts, and that will very quickly, in my opinion, drive utilization of the most advanced silicon, because once you have something smart, making it smarter is very high return.
So what you're talking about here is basically finding the horizontal connections between a lot of vertical markets.
Yeah, and the question is, how horizontal is it? Because the PC was unbelievably horizontal. Right? Smartphone was quite horizontal, it turned out to be. I think it is possible that now the applications become a bit more vertical, and that's why I'm saying it's well possible that a lot of the silicon gets optimized for a more vertical application. Or it's also possible that a category of digital algorithms become generic enough so that they can be applied to different fields. Right now, I don't quite see how the algorithms to win the Go game immediately apply in the same packaging to driving your car and to do some bio research. But it's there's going to be a lot of cross-discipline virtualization here.
It's a new kind of efficiency that we built into Moore's Law over the years, right?
I think so. I like to use Moore's Law no longer as talking about transistors. I think Moore's Law should be just the acronym, or the word we use to refer to exponential impact. That is really what we're after, right? And I think we have a wave of that's possible ahead of us.
On that, I'd like to say thank you very much for a wonderful conversation.
Thanks for having me.